on this end we have time, okay? And we're going to have that time increment so small, we're going to pretend that there could only be three things happening. Stock price is going to remain the same, it's going to increase slightly, or it's going to decrease slightly. Again, it's a model, but if that delta T is so small, you're not losing much. And next period, follow these. These are called nodes. Okay. So from here, I can go same, up or down. Up, same, down. Now I have 5 possible prices. Next period, you're going to have 7, 9, and so on and so forth. I mean, I'll do just one more. Suppose this is the end, okay? At that end, you know exactly what the prices should be. Then you're going to ask yourself, what if I find myself here, this is period 1, 2, 3, at the end of period 2. Prices can go up a little, remain the same, or go down a little bit. In those cases, I know the value of these, right? Let's call this VU, VN, V down. There is a way we can attach probabilities to these moves, okay? Because it's so small, and given that we have an assumption about probability distribution of how prices move for small periods of time, we can calculate the expected value over here. You know, what's the expected value if I'm here? Well, since it's a little bit in the future, I'm going to also discount it. Then I'm going to find the price here. Then I'm going to ask myself, what if I find myself in these prices in period 1? Same deal. Until you reach this point. If you're careful, and the program that you're using is good at what we call garbage collection and computing. In object-oriented programming, you can write this as an object a tree. A tree has nodes, and each node has an up node, mid node, down node. Once you determine the object of node, all you have to say is there's a value function. Value function is discounted expected value of up node, middle node, down node. Once you define the node object, all you have to say is, okay, let's set the values of the final nodes. And internally, you have the structure. All you have to say, give me value 0, 0. That's it, done. But Excel's VBA is horrible in garbage collection. If you do this for 10 steps, it doesn't have a problem. If you try to do it with 100 steps, it is so bad because it has to go recursively. But we can do it using arrays, which we're going to do for American options. It's not that complicated. The more time steps you have, the more precise you are to the results. Typically, if the strike price is close to what the price is now, 100 steps is more than enough. If it's too outside, maybe, 1,000. But in this day and age, that doesn't bring too much work. And the number of nodes, maximum number of nodes is 2 times the number of steps plus 1. And obviously you have more of those. At most, you have 1,000,000 nodes. Calculation of those, I could do it back in 1980s on a little PC that had 256 K of memory. These days, it's no problem. If you want really precise, do 10,000. Okay? We will work on how to get those done. And there are also other methods. But the important thing is, as long as you have a way to calculate the value of the contract at the boundary, you can go all the way back. This doesn't necessarily work for all of them. For example, there's a contract called Asian options. What the value of the option at the end depends upon the average of the stock price during the life of the option. But the trouble is you can reach a given average from infinitely many different points. So that would be what we call strongly path dependent. You can't solve it with this, but we have other methods. For example, we can do that using what we call Monte Carlo simulation. What we're going to do in that case, take this equation of motion. We're going to make delta t so small. We're going to simulate price paths. At any time, this thing is going to be random. We're going to randomly generate it. For a given path, I can calculate what the value of that derivative contract can be, as long as it's not American type. For that contract, for that path, I'm going to calculate the average price during the path. Compare it to the strike, the value. But that's one possible realization. We're going to do this 10,000 times and get the average of those. That is actually a very good approximation to the value. There is, of course, some randomness involved, sampling errors, but then we have beautiful ways to reduce those sampling errors. Now, I'm going to only write the formula. I'm not going to do any Excel today. Monday, we'll do more Excel. If C is a European call option on a non-dividend paying stock, then Black-Scholes equation can be solved analytically. That doesn't mean I can do it, but somebody pretty smart named Einstein has already done it, where C is S times N of D1 minus K times and we're going to write down what these are. Price of underlying now. K is the strike price, aka exercise price. If you're into American baseball, you pretty much know why I picked K. Because in baseball, a strike is represented by a K. R is so-called, let me write T first. T is time until expiration expressed in years. R is so-called continuously compounded interest rate, or you can think of e to the negative RT is equal to present value of $1 that is due at time t. So if you're using a regular interest rate, if you think about it, R is equal to or negative RT PV1, let's call it. So R equals ln of PV1, what should we call it? T. If you're using regular interest rates, for example, if R star is an APR, okay,